Okay, I think we're ready to go here. Thank you very much for the very kind introduction. I can understand a few words of it, but I'm sure it was very good. Apologize, I can't speak in Korean, otherwise I'd be happy to do it. So you'll have to take my broken English here. So it's a great honor for me to be here, to see a number of old friends, former students, and good colleagues. I think this comes in and out, but it's okay. The lecture that I'm going to talk about today is, the title shown up there. We've been interested for about the last 3 years in materials for fuel cells. And it's been a very fruitful area, which quite a number of students and postdocs have worked with me on. So I'd like to give you a brief overview today in about the 30 minutes that we have here. Thank you. I've got the microphone fixed, if I can figure out get the pointer, I'll be in real good shape. Now we're under control. Next slide, please. There we go. Well, let's tell you where I come from. I come from the state of Virginia. Most of you are familiar with Washington. We're down in the southwest part here. Next slide. Next slide. This is a view of our campus. We have quite a nice, beautiful area in southwest Virginia. It's 27,000 students, so it's a large university. It's quite a small town, Blacksburg. This is the motto of our football team, which is the number 4 in the country right now, so they're doing better than the chemistry department, I'm afraid. Next slide. This is a river called the New River. It's supposed to be the oldest, second oldest river in the world after the Nile. I guess I didn't do the carbon dating, but it's a very pretty area. This is the Appalachian Trail, so we hope that you'll come and visit us sometime there, as I've been to Korea many times now. Next slide. Today I'd like to go through some of our work quickly in the area of fuel cells. We've been quite active, and it's tough to summarize it in 30 minutes, but I'll try to give you a little bit of background and what our objectives are, and a few results, and a few conclusions, and some of the things we're doing now, and I'll thank some of the people who've done the work. Fuel cells have a lot of potential in a number of different areas as a environmentally friendly energy source, particularly for cars and houses. And not only cars and houses, but also portable power. There's a very nice website here, if you're interested. We've been working with people at Los Alamos now for several years, and I've had quite a bit of interaction with them. I've had students down there and visitors up at our place. So we're interested in both hydrogen air systems and direct methanol systems. Next slide. A little bit of background for people not familiar with the area. This shows a sort of a single cell, and the single cell now has an anode, and it has a cathode, and it has a film in the middle, which is known as a proton exchange membrane. And the film here has a number of requirements, but essentially it has to be able to transfer H plus from the anode to the cathode, and allow the electrochemistry to proceed. Usually in the presence of platinum catalysts, or platinum ruthenium catalysts, other types of catalysts. Has a number of other special requirements as well, including pretty good stability, both under highly acidic conditions and also under fairly oxidative atmosphere. Next slide. This is a picture of a truck that General Motors let me use. I visited them earlier this year. And an example of a prototype truck. There are many organizations around the world that are certainly involved in these. But this indicates the propulsion system, in this case in the back. And it reminds me that the individual cell is called a membrane electrode assembly, or MEA. And each one of those individual cells can only generate about 1 volt, or actually less than 1 volt. So in order to make something work like an automobile, you have to link them together in what are called stacks. And you can have 10 or 20 stacks for portable power. You might have 100 stacks or even 200 stacks, maybe to run an automobile. So it's really quite a detailed systems engineering above and beyond the part that we get involved in. We get involved with the proton exchange membrane for the MEA, and also to some extent the materials for the catalyst layers in the anode and the cathode, because both of those also have a polymer of the order of 10 to 20, 30 weight %, which serves the purpose of both as a proton conductor, and it also has a mechanical strength effort that needs to be utilized. So this is one example. Next slide. If we could back up one, please. For many years, as a number of you know, the material that has served the purpose of the proton exchange membrane in fuel cells has been this copolymer, particularly the one developed some years ago by the DuPont company known as Nafion. It's a copolymer of tetrafluoroethylene with this vinyl ether comonomer, about 13 mole % to an equivalent weight of about 1100. So it's known as Nafion 1100, which corresponds again to about 13 mole % of this comonomer. It's actually polymerized in the sulfonyl fluoride form for a variety of reasons, and then converted into the sulfonic acid. So this is the ion conductor. This is the proton conductor then that has, again, the role of getting H plus from the anode to the cathode. It's excellent material. It has very high conductivity, very stable material with the carbon-fluorine bonds, and certainly is capable of the long-term stability. It is a relatively soft material, though, and as you go up in temperature, it gets even softer, and if I have time, I could show you that the hydrated TG is only around 100 degrees C. So it gets a little soft at the temperatures that one would like to use it. It has, for methanol type systems, really too high a methanol permeability through it. So methanol is a fuel, so you can lose a lot of the fuel by short-circuiting, as it's called, or methanol crossover. And it is, at the present time, a fairly expensive material. Maybe it'll be cheaper in time, but right now it's pretty expensive. So we have a number of objectives on the next slide to try to identify some alternate viable proton exchange membrane systems that might be of interest not only as the film itself, but possibly as components in the reactive catalyst layer electrodes. In particular, we have been reproducing behavior at 80 degrees C. 80 degrees C is currently about the limiting temperature. So when one talks about high temperature PEM membrane systems, maybe we could just say higher, because if we could get to 110 or 120, it would have some real advantages. If you can go to higher temperatures, even 110 or 120, then you can avoid problems with contamination. Carbon monoxide in all the fuels, whether it's hydrogen or gasoline reformed or methanol, carbon monoxide can poison the platinum catalyst. And if you can increase the temperature to 110 and 120, then the poisoning is reversible. And you can then keep the system going quite well, even with higher concentrations of carbon monoxide and some other impurities. So that's one of the driving forces. Another driver here is that the cathode reaction kinetics, the rate controlling step, they're about 10 times slower than any of the rest of the system. And thirdly, from a systems engineering point of view, if you could do the reaction at 110 or 120, you'd greatly simplify the systems engineering for integrating these stacks together to make automobiles and other systems. So that's the driving force for higher temperatures. To work with portable power, the direct methanol systems are of interest. And direct methanol is currently quite a dilute solution of methanol and water, as I'll show you. And one reason why it's so dilute is that the permeability of the methanol through the Nafion films is really too high. So one major objective here is to try to make adequate systems that will have lower permeability in methanol. Well, I've been involved in these materials for quite a few years, since my industrial days at Univ Carbide, where we first commercialized these systems actually a long time ago. They've gone through various owners. The current owners are Solvay Advanced Polymers systems. But they have quite a number of good properties, and the last one is of interest too. There are now multi-million pound a year plants that are able to make several of these monomers. Next slide. Well, a lot of people around the world have been interested in the possibility of using the polysulfones and polyketones as precursors for making these proton exchange membranes. And nearly everybody has done a post-reaction on the existing polymer. And if you do a post-reaction, the well-known organic reaction, electrophilic substitution, sulfonation, you can put sulfonic acid groups on the backbone, and they go predominantly in this region. And they go on okay, but they go on pretty randomly. And it's fairly tough to control the composition closely enough to keep the morphology where you really need to have it. We've chosen to go a different direction. We've chosen to put the sulfonic acid units on this part of the molecule. And by doing that, we think we have several advantages. But in order to do that, we have to prepare another monomer, which we've done. Next slide. The monomer that we have worked out is one that is actually known in the literature, several references, but we've polished it up a bit, so we can make this a precursor now. And what we do is then make a copolymerization between this monomer and the unsubstituted system to make a rather precisely defined material. There's a number of advantages here. I won't go into many of them. We have been able to get higher conductivities. We can get conductivities that are 5 to 10 times higher than one gets from the post-reaction. And we think that's related to the enhanced acidity, and also perhaps due to the fact that we can have two closely associated sulfonic acid units on the molecule. Next slide. Well, the polymerization can be conducted as has been done for many years, except that we introduce now the comonomer. So we copolymerize the unsubstituted activated halide and the substituted activated halide with a wholly aromatic bisphenol in order to maximize some of the stability issues. This is an experiment that's currently being published here, where we have capped the end group, so we can do this to estimate the number as molecular weight. We heard a lot of nice talk about molecular weight in the previous speaker. These types of systems are not so easy always to characterize by chromatography because they sorb on the columns unless you develop some special columns, which we've been able to do recently. But we can do end group analysis. We can put these tags at the end of the molecule, and we can do NMR spectroscopy at 500 megahertz or even 400 megahertz, and we can get a pretty good estimate of the molecular weight. So we've done that. In fact, there's a publication that's in press right now. Next slide. Well, in our brief discussion today, I want to show you the repeating unit. The repeating unit consists of a random copolymer where we have the hydrophobic part and we have the hydrophilic part. And it is pretty random because during these polymerizations, one gets what is well known to be ether-ether interchange taking place between the activated aromatic ethers. Well established, I won't go through that with you today. But the acronym that we've developed is to call these materials BPSH, where this is the hydrophilic part, and the 30 to 40 refer to the mole fraction of the sulfonic acid moieties. So when we say BPSH 30, it means that it has 30 mole percent of these features. Next slide. Well, the system has pretty good stability. The sulfonic acid salt is very stable. The free acid, as we expected, is less stable than the salt, but we're interested in using these materials down at 120 or maybe 150, and so we think that the basic thermal stability here is adequate for that purpose. And in fact, it's in the same region that Nafion begins to lose weight also. Next slide. Go forward, Drew, please. Yes. Well, we make these copolymers in basic form. We do nucleophilic substitution polymerization, so we come out with a sulfonate form. And in order to use them in proton exchange membranes, they have to be in the acid form. So we've investigated two different ways of acidifying these films. One is at room temperature, one is by boiling it. And we started the first methodology first. Later we found that by boiling it, we could enhance the conductivity significantly. And it does not change the chemical structure. I won't go try to prove that to you today, but we proved it to ourselves. What it does is actually alter the morphology a bit, and I will show you a little bit about that. So the boiling method then we call method 2, the room temperature method we call method 1. Next slide. Well, we can cast nice tough films from these materials, and they're typically 40,000 or 50,000 number atomic weight or higher, we think. So we can cast films and do dynamic mechanical measurements. Here's a control, and with 30, 40, 50%. So we get some relaxations here, characteristic of some of these early ethers, which we've worked with for many years in the past. So this further shows that the materials basically have some fundamental mechanical stability. They're quite robust. Next slide. The TGs of the unsubstituted materials are around 220, and by increasing the sulfonic acid moiety, you increase the TG quite a bit. And there's a difference whether you acidify the material at room temperature or whether you acidify it under boiling conditions. I won't go into great depth, but primarily we've been interested in the enhanced conductivity that one gets by method 2. Next slide. Well, to measure the proton conductivity, we've done 3 types of measurements. You can do impedance spectroscopy, following procedures established by our colleagues at Los Alamos. Dr. Yusum Kim in my laboratory has built a high-temperature device which allows us to measure conductivities at elevated temperatures. And then we've made actual fuel cells. And the fuel cells are often called MEAs for membrane electrode assemblies. Anode, cathode with a laminated film in the middle, so it's adhesively bonded in quite stable ways. And then you can use either the commercially available electrodes or you can use the new electrodes. I don't have time to tell you how we've done this, but we make dispersions. And we make dispersions and combine them with the platinum and dry them down and make anodes and cathodes. To a first approximation, you can get a pretty good result actually with the commercially available Nafion electrodes. We think over time we'll be able to probably do a little bit better by using some of the homemade electrodes. Next slide. This is a device developed by my good friend and colleague Tom Zawazinski. So this is the impedance device. We measure resistivity and we calculate conductivity. Next slide. This is a device that Dr. Kim in my lab developed for measuring the conductivity at elevated temperatures in water vapor. Next slide. Well, most of the effort that has been scaled up so far has been with the biphenol-based sulfone copolymers. I wanted to tell you, though, that can't have all the students do the same thing. So we have a number of different copolymers that we're investigating: airline ethers, airline sulfides, wholly aromatic systems, partly aliphatic systems, fluorinated systems, sulfones, ketones, and phenylphosphine oxides. So there's quite a variety of results, and I'll just show you a couple. Next slide. In view of time. This is some conductivity measurements, effective sulfonation and conductivity for either the polyairline ether sulfones, and of course the level of disulfonation influences the conductivity. We get pretty similar results actually for the thioether sulfones that are substituted. And the standard of comparison here is the Nafion 1100 series, which is able to generate a conductivities of about 0.1 Siemens per centimeter. Maybe some of you prefer 100 millisiemens per centimeter. So we can match that quite easily at around 30, 40, 50% composition. In fact, it looks like we could exceed it. And you might say, well, why don't you go to the highest conductivity that you can get? Next slide. Well, there's a problem with that approach, and others have run into this, but I don't know whether it's really been recognized so much. What you find is that, here's a reference to our work in Journal Membrane Science in 2002. If you increase the concentration of the ion conducting sites, the water absorption increases, but then it really exponentially increases at some point. This is a general phenomenon, and so we have strong films down here and very weak sort of hydrogel type films up there. So you cannot in a random copolymer go to as high a level of conductivity as you might like, because you lose the balance of strength and conductivity. It's a general phenomenon. It occurs with the substituted peaks as well. Next slide. We've begun to investigate how this relates to the morphology of the cast films. And here we're showing you some data, a tapping mode, atomic force microscopy. as a function of the control 20, 40, 50, and 60. And under these conditions, which correspond to method 1, the room temperature acidification, you can begin to see the dark regions here we think correspond to the sulfonic acid plus the moisture that it picks up. We don't intentionally put moisture in, but it does quickly pick up some moisture. So the dark regions then are probably the softer phase. And in fact, you begin to see sort of a percolation limit. If you recall what I showed you a few moments ago, that these have 30 or 40% water absorption, and this one has maybe 200%, then what we think happens here is that you get a phase inversion. So you get a phase inversion where the hydrophilic part becomes continuous, and the hydrophobic part has lost its co-continuity. So these are very weak films. These are quite strong films, much stronger than Nafion, as a matter of fact. Next slide. You can hit both, if you would, please. This shows the conductivity of our copolymers as a function of temperature over this range. It has 3 different compositions. It has a 30% copolymer, a 35% copolymer, and a 40% copolymer. And it has been acidified under the 2 conditions I mentioned: room temperature, method 1, 100 degrees C, method 2. What you can always see is that method 1 has a very high activation energy. Method 2 is a lot lower. And of course, as you go to higher concentrations of the sulfonic acid sites, the conductivity is quite good. Even at 35% over here, if you go to the boiling conditions, you can see that there's very little hysteresis in conductivity. So we like very much now the copolymer composition of about 35%. We've scaled that up recently. Next slide. These are at 100% humidities, I should mention. I wanted to put a couple points in on the methanol fuel systems here. Time is going quickly. So in the direct methanol systems, a fairly dilute solution is used currently. About 1 molar, which is only 3.28%, sort of like windshield wiper fluid, or even half molar sometimes used. That's because of the high permeability of the Nafion. What we can do so far is show that we get performance curves that are at least comparable to the Nafion, probably a little bit better. And one reason is that the crossover current measurements that can be done will give you an indication that the permeability is much, much lower for our copolymer, which is desirable. And then in the next slide, I have a sort of a cartoon to illustrate that. You go to the next slide. If the methanol permeates the film and goes from the anode over to the cathode, it may get oxidized at the cathode. And if it does, it sets up a backward process, which is referred to as crossover current or short circuiting. And so low permeability is very desirable. So we seem to have a factor of about 4 lower permeability than the Nafion, which is quite desirable for these direct methanol systems. Next slide. You can begin to see the voltage versus current curves as a function of copolymer composition. And so the 35 system is quite good here. This is the control Nafion. This is used for maybe a laptop computer, or with some installation, maybe even a cell phone. So we think that these systems have some quite attractive properties for particularly direct methanol fuel cells. Next slide. I wanted to show you in these 3, you can hit all 3 if you would please, the atomic force microscopy for the room temperature, 100 degrees C and 140 degrees C. So you can see that there's very much more of an open texture that's developed. So it influences the morphology. It does not influence the chemical structure. You'll have to take my word for that. This is for the 40% copolymer. There is an irreversible deformation that can be observed at 140. And that turns out to be, we think, because you're essentially approaching, maybe exceeding the hydrated TG of this particular system. Next slide. We hit all 3 of them again. This is now the 35% copolymer. And there is some difference between room temperature and 100 degrees C acidification, but a lot less. And there's a lot less deformation at elevated temperatures. One reason for that is that the hydrated TG here is at least 140 degrees C. Hydrated TG we found for Nathion to be about 99 degrees C. So there can be quite a difference if one is attempting to get to this 120 to 140 degree type of performance. Next slide. Well, everybody's always interested in aging, and as I'm getting aging myself here, so am I suppose. But we have several different ways we do this. We can accelerate it in steam, but what people really like to see is that you make fuel cells and then see how long it lasts. Well, we haven't done as much as I'd like, but we have done a month here at least. There are different requirements for different applications. For automobiles, it might be several thousand hours. For some of the portable devices and for some of the military devices, this is already exceeding some of the time, the limitation goals that were set. So we're going to continue this and hope we can get a few thousand, but it certainly hasn't failed yet. Next slide. Here's a little plot to show you that this is the fuel cell type measurements. This is 30% copolymer and reasonable conditions, we think. And the suggestion is that there's very little change in the resistance under these conditions. Next slide. Time to finish up here. I'm already getting low on time. So let me summarize a few things that I tried to tell you in this brief overview. We have identified a new series of copolymer membranes that have some interest both in hydrogen air and in direct methanol air fuel cells. We think that there's some real promising results that have been observed in some of the methanol systems already. We think there's more that can be gained here. We're in the process of investigating different types of electrode attachments, different types of dispersions. That's sort of where we are at this point. The cathode remains the most challenging area, but we have a fair amount of confidence that further progress can be made. Next slide. You can hit them all here if you would. We have successfully scaled these to kilogram quantities, both the monomer sulfonation and the copolymer sulfonation, and this in fact has been generated now for several people to evaluate. On the fundamental side, we're working with this to further define the morphology. We have, in fact, a couple of visiting professors from Korea with me now that are making sulfon-imide systems, which are more acidic, and they actually have higher conductivities for a given copolymer structure. We found a number of new ways to make MEAs by aqueous dispersions, and I continue to have an interest in block copolymers. I want to thank the people that supported it and did the work, several organizations, the National Science Foundation, Department of Energy, the Army Research Office. Next slide. I want to thank the people who did the work. This guy did nothing. Certainly want to thank Dr. Kim, Dr. Yusung Kim, who's been a tremendous colleague for the last 3 years. He's possibly going to leave me in a while for something better probably, but I'll really miss him when he's gone. And I certainly want to point out Dr. Hong was in the audience as well. I didn't talk so much about the polyimide work today, but Dr. Hong did a really nice job with me too in that area. And we have a publication that's about ready to come out on that work. I think I had one last one actually. Forgot to, Professor Gibbons helped me out here. I had one last one. That is that we're organizing a workshop in this area on the materials for fuel cells. If you'll send me an email, I'll be happy to send you the program as far as we have it so far. It's in Silomar, California, near Monterey and Carmel. Nice time of the year. It's pretty cold in Blacksburg about that time of the year, so we'll see if we can't get out to the West Coast there. So we hope that some of you might be able to come over there and join us. And in closing, I want to thank very much the organizers for inviting me. It's been always a great pleasure to come back and see old friends in Korea. Thank you very much.